G'day viewers. In this segment we'll talk about the spanning tree algorithm, which will complete our understanding of how LAN switches work. Okay, so in the previous lecture I talked about switches, modern switched Ethernet, how hosts were connected to them, and how they forwarded frames, so thus providing connectivity between all of the hosts. But a major assumption we made was that the topology and the way these switches were connected could not contain loops. Now I'd like to talk about how we can allow these switches to be connected in ways that do contain loops and still have the overall system work. There are a couple of reasons you might want to have a loop in the topology. You might simply want some redundancy in your network. You can see here on the diagram on the right, I've added a redundant link in the middle between the two switches in the middle. You might do this simply because one of them might fail and you'd like to provide a little bit of redundancy ahead of time, so there is that if there is a failure, there are still links in the network so it can work. You might also make a simple mistake. Networks evolve over time. I think components are always being added and removed, and it would be very easy for someone to plug a cable into the wrong port and inadvertently create a loop. This could happen, and we wouldn't want a simple mistake to take the whole network offline and have it not work. So we would really like for these LAN switches to just work, to provide very much a plug-and-play environment. LAN switches, in fact, are some of the earliest sort of plug-and-play computer networking that just works. I guess Ethernet does too, but LAN switches are really an extension of that. We also want to do this. One of the constraints for the design of LAN switches, Ethernet switches, was that the switches should work with no change to the hosts. So we don't want to have to go and upgrade all the software in millions of hosts just to be able to connect switches with loops. But if we don't do something compared to what we've seen so far, we have a major problem with loops. Let's look at that for a minute. What can happen? So suppose that the network is started and we have our network here. I've labeled the hosts A through F. What's going to happen? I think I'm just going to override on this diagram and draw a series of frames being sent. A sends to F. Well, at the beginning of time, no one knows where anything is, so they're just going to broadcast frames. A's frame goes into C. C gets it. C will broadcast, so it will send it out the other ports. That's what we've got to do initially. Okay, so it went to B and it went to D. It actually went to D twice because we have a loop in our topology. D, well now let's just look at the first of these frames it gets. Consider the right one first. D will get that frame in and then it will send it out everywhere else to F, to E. It will also send it back to C on the other port to C. Oh boy, you can see that things are going to go a bit south here. D will look at the second frame that it gets. This is from D on a different port. Now it doesn't know this is the same frame. You might think we could just look at the contents, but you don't know whether this is a second message from A or not. We really have no way of telling. D will then send this frame out to E and F, and of course up the other link back to C. Wow, E and F are now not so happy. They've now received 2 copies of this, and they didn't want, well, at least E didn't want any of them. But we're not done yet. We now have these 2 frames that have gone to C. Let's look at the one on the left. It went to C. What does C do with it? It broadcasts it because it still doesn't know where F is, hasn't seen any frame from F. Goes out to A and B and down to D on the other link. And similarly, for the frame from D to C, the second one, it will come up, go out to A, B, and down to the other link, back to D. Now, this diagram is getting very messy. If you follow some of the logic through, I could write all this down. I think I'll do that on the next slide. You'll see that we have something nasty going on. I'm just going to draw a big massive circle here. Some packets are spinning around here left to right. There's another series of packets spinning around here in another direction. And traffic has been forwarded out to all of these nodes, A, B, E, and F, as we go around this loop. So we have a storm here in the network. One packet was sent in by A. It never ends. Traffic keeps going around the network and fresh copies of packets have been delivered to all hosts on the edge. This is really nasty. Wow, so here is just the beginning of that logic spelled out for you a little more in terms of who sends where so you can follow it through. and it just goes on and on. It never ends. So a forwarding loop here has caused something pretty nasty to happen. The solution that we'll come up with to prevent this problem, and we would really like to nip this problem in the bud because you can see that one packet can cause devastation here with the loop. The solution we'll use is for switches to collectively find and agree on something called a spanning tree. A spanning tree of the topology. A spanning tree is simply a subset of links of the topology, which is a tree, so it has a root and branches out from the root, but it has no loops in that topology. The subset of links in this topology is a spanning tree if it's a tree, and it spans the topology. It reaches all switches, so it will allow us to deliver frames to all hosts on the network. Once we find this spanning tree, this is the first step, the thing we want to do, then we simply use it as before. Switches simply forward frames along the spanning tree. So they just pretend that the topology was only the spanning tree. If we know which way to go, great, it'll get there. If we don't, we're going to broadcast. And if we broadcast on the spanning tree, frames will tend to go up the spanning tree to the root and then down all branches, so they'll get everywhere, but they won't loop. This sounds pretty messy with spanning trees, so let's just look at some examples to get a sense of what a spanning tree is, and then I'll talk about the algorithm to find one. Here on the left, we have the topology. This is the links which were physically installed in the network. Now I want to talk about some spanning trees. Usually there are many different possible spanning trees for a network. Let's just see some of them. Let's just pick a node here arbitrarily, top left one, as the root of a spanning tree. How are we going to create a spanning tree? Well, from this root, let's create some branches. Let's say I go down here and here. And, I'm just going to say there are only 2 branches in the tree. So from here I'll go up to here, and from here I'll go over to here. This then is one spanning tree. It reaches all switches in the network. I can cross out the links we haven't used. Okay, fair enough. Here's another spanning tree just to show you that multiple ones are possible. I'll select a different node as the root. From here I'm going to just arbitrarily pick one branch down. And from here I'll divide. I'll just say I'll use this other branch here that's going to reach these switches, and a different branch here will reach these switches. In this spanning tree, I don't use these 3 links of the topology. These are all different possible spanning trees. Of course, in our automated solution, we're only going to want to choose a single spanning tree and have everyone agree which spanning tree we'll use. Here's that same diagram cleaned up. You can see, it looks like in this example here, sorry, I chose a slightly different spanning tree. This is just yet another possibility. Instead of going here, I went over here. Okay, well that just shows you yet another spanning tree. But conceptually, the point is exactly as I'm saying. Okay, so now we need an algorithm to find the spanning tree. We've seen there are a few. I can't even agree amongst my slides on which spanning tree is which one. But we want all of the switches to find a single spanning tree. Then they can use it. How are they going to do this? It's a little complicated or subtle, again, because this is a distributed game. If someone like you or I could just see the network, we could draw a spanning tree and say, here, use this. But the switches can't do that. They're distributed. Firstly, every switch runs the same algorithm. There's no special distinguished switch which is in charge. This is actually helpful because then there's no switch that can fail and throw your network into chaos. All switches can handle what's going on in the network. These switches are going to start with no information because we don't want to have configuration or make assumptions. Now, switches can only see what's going on with themselves. They can send and receive messages, but they don't know what's happening elsewhere in the network, just what they hear and what they send. In fact, all of the switches are not only doing this, but they're operating in parallel because they have no way to otherwise coordinate their actions with other switches. As they operate in parallel and send messages, we want these switches to continually search for the best solution. If we do this, we will end up, if we can solve this problem, I haven't told you how to yet, we will end up with a highly robust solution. It will work for any topology with no configuration because we assume that we start with no information and have no special switches or position in the network. It will also adapt to link and switch failures. And the reason that we will try and do that is that we'll have the switches continually search for the best solution. And we'll have them throw out information about nodes that's not repeated over time. So if there's really old information about a switch that you haven't heard from for half a day, you'll eventually forget that and find the best solution in the network that you believe exists now. And that way, if some component fails, you'll converge to another spanning tree which uses the nodes that are in the network and cut over maybe from a failed link to another redundant link. I'm getting a little bit ahead of myself. Let's work through some examples to see this spanning tree algorithm, because if you haven't seen algorithms like this, there's a lot to it. Don't worry, we'll work through an example. Oh, and I'll just tell you that the spanning tree algorithm that I'm going to go through was pioneered by Radia Perlman. She's shown here, you can see her picture. She did much of the early work on different kinds of spanning tree and early routing protocols in the internet. She worked on different kinds of routing in the internet, the spanning tree algorithm we're going to look at, and also different kinds of link state routing, in particular link state routing that we'll look at when we get to IP networks. Nowadays she works on network security. But what we need to go through now is the spanning tree algorithm. Here is an outline for that algorithm. These are the steps that will happen. First of all, to come up with a particular spanning tree, we need to elect a root. The root could be any node, that's possible. They just need to agree on who it is. So we're going to let the switch with the lowest address be the root. So switches can use their addresses to look and send messages and agree on who's the root. When we have the root, we are going to grow the tree from the root using the shortest distance from the root as a way to decide what branches are on the tree. If we have ties, because from one particular switch you could get to the root by two different paths of equal length, we will again use the lowest address as a tiebreaker to decide which branches are on the spanning tree. And when we have the spanning tree, we'll then simply turn off any of the links, the ports, which don't forward onto the spanning tree, and we can then use the spanning tree to forward using our learning algorithm. Now, actually, one thing that's slightly complicated is that steps 1 and 2 happen in parallel. There's no phase 1 and then phase 2. This kind of logic is interleaved. Whereas once things have stabilized, then we proceed with turning the ports off and using the tree for forwarding. Okay, now in a little more detail, I've said what these nodes want to do. Find the lowest node, grow a tree out from that node. But they do that by sending messages. So here's a few more details on the messages they send. Initially, each switch is going to believe that it's the root of the tree in its messages. And every switch is then going to follow this same behavior. Every switch will send periodic updates to its neighbors. These updates will contain its address, the address of the root, and the distance in hops to the root. So an example is shown below here. Here's switch C. It's sending out a message. It might say to its neighbor, "Hi, I'm switch C. You know, I've heard that there's this great root of the network called A, and it's 2 hops away from me." We will abbreviate that message as CA2 when I write down what happens, or the state of a switch. Now, all different switches are going to get messages from their neighbors, and they're going to process them. When they hear different messages, switches are going to update their configuration, and they will favor ports which reach better routes, lower cost routes with shorter distances, again using lowest addresses as a tiebreaker. And it's quite amazing, really, that if all switches follow this simple process, this rule, this 1-2 punch rule, and update, the network as a whole will converge to a single shared spanning tree. Wow! Okay, let's see how that could happen. This is kind of tricky stuff. We do need to work through an example to see what's going on. Okay, so in the beginning, I've labeled all of the nodes here of the simple topology with their state. Everyone thinks they're the root, and they're distant 0 from the root. Now, in every round, all nodes send out messages to their neighbor with their state, and then they receive the messages from their neighbors and update their own state. Let's look at the kinds of messages that are sent out. I'm just going to pick one node, node C here. So node C, this is its state. It will send this message out, all of its links, to nodes A, B, and D. D twice. They'll all get these messages. And similarly, every other node will send that information to its neighbors. Having got that information, they'll then update. Node A, for instance, will hear from node C, but A will say, well, my state's better, I'm a better route. Node B will get messages in from node C and node F saying that they both think they're the route. And node B will sort of say, well, rubbish, I'm a better route than either of you, so I'm sticking with my state. Some people will change though. Let's imagine node E. Node E will send out and it will get messages back from D and A. Well, guess what? A is lower than E. D is lower than E too, so E will actually hear two better messages. The best one is A. So E will be forced to update its state. It will say, oh, okay, well, I'm still E, but I've heard this is route A, and I am distance 1 from it, since I got a message from A saying it was 0 hops away. Similarly, there are going to be some other updates. C is going to update to say C, A1. C now thinks A is the route and it's next to it. D will also update. D will actually think the best thing it hears here is from C. It thinks it's next to C1. Now I can also see here that F will update to be F. It will hear from B as its best option and it's 1 hop away. So that is the new state of nodes. Let's go to round 2 now. Round 2, I've replaced the diagram, I've updated the state of nodes. All of the nodes send these messages out to their neighbor. So C sends the message CA1 out to neighbors A, B, and D twice, for instance. What's going to happen? Well, A still sticks with its configuration. It's the route. No one can beat it. B, as it gets this message from C, let's see here, unfortunately, B learns that it is not the best option. B will update its state to be B, A, 2. It's 2 hops from A. A is a better route than B. And it's going to reach the route through C. C is going to keep its state. It won't change. D will actually update too. D will hear from both E and C that there is a route A. In fact, D could get to the route A via 2 different routes. It could either send via C to A or E to A. D is going to decide that it will send via C to reach A because C is a lower address than E. And D's state is going to update from DC1 to DA2. And I think everyone else is about where they were. Okay, so here it's cleaned up. Third iteration. Everyone sends out their state again. We process the received messages. What happens? Well, this is a lot of work. How long can this go on? We'll see. Okay, A and B, and actually C and D remain where they are. Now you notice here for D, I've said that D is going to reach the route via C on the left-hand side. There were 2 possibilities. Actually, both of these ports will have addresses, so D will be able to choose the lowest port. That's just a quirk there. E, yep, E stays the same. F, however, is going to update. F is going to hear that there is a better route because B sent this message out saying, oh, I'm B, and there's this route A, I'm 2 hops from it. D actually will also send a message out. And F will update its state to be F, A, 3. Okay. Well, I think we've finished now. Let's see. Yep, so this steady state has been reached. Every node will now continue to send out its message, but nothing will change. When nothing changes after a while, everyone knows that we're done. And you can see here I have grayed out and we can turn off these links. They're not, in fact, used for forwarding. The algorithm will continue to run and it will time out information so that, for instance, if node A fails, then eventually other nodes, switches here, will discard the messages from A and forget about it because it really doesn't seem to be there anymore. B will become the new route, and that new spanning tree for B will be computed and then used. We can see how the spanning tree is used. Forwarding proceeds just as usual according to the backwards algorithm, the backwards learning algorithm. So let's see that the network's just been turned on. D wants to send to F. What's going to happen? Okay, well, now since no one knows where anyone is, everyone will broadcast and forward out all ports. We're only going to use ports on the spanning tree though. That was our restriction. So D sends to C, C sends to A and B, A sends down to E, B sends down to F. Got it, we've reached F. Now, when F sends back to D, we're going to proceed along the reverse path because now this switch F knows that you get to D through here, and A knows that D is down here, and C knows that D is down here. We're more efficient sending back from F to D in that we did not broadcast over our spanning tree, so we didn't reach all switches on the network. Nonetheless, you might have noticed that we didn't really use the best route. There was a link here between D and F, but our spanning tree didn't include it, so we didn't get to use it. This should give you a hint that we can do better than the spanning tree. And we'll see how when we get to the network layer and think more about routing, we can come up with better algorithms. Nonetheless, the spanning tree algorithm works well in that no hosts were changed, yet we've solved this problem. It's completely plug and play and we can handle any topology. This slide cleans things up, just shows you some of the transmissions in different colors. I don't know why. I think I see one error here. There are two errors here. I'm just going to cross one off. There should only be one. A will only send to E once. I've written down just the transitions here so that you can see them. So the forwarding, so that you can see it. And if you're sort of wondering how you would remember all of this, here's a poem, an algorithm that Radia put together. She came up with the spanning tree when she was at DEC, and while it initially seemed like a very difficult task, it proved to be easier than she thought when she worked out how to think about it. She did that in the early part of a week, and it gave her enough time to write a poem in the rest of the week. So there you have it. You can see this algorithm. And now you know how LAN switches work.